Hello everyone. Today in this chapter we are going to talk about the stream transport from mountains to oceans. There are different types of fluid flow. Laminar flow are the types of flow that requires a slow velocity and a smooth flowing surface. And a good example of laminar flow is a cup of water poured onto a table. That the water flows on the table is a laminar flow, that all the streamlines are parallel to each other. Turbulent flow means there are eddies in the water, and the flow velocity usually fast, and the bed of stream is not smooth, and therefore the streamline of the flow is random and impossible to predict. So in reality, most of the flow of rivers are turbulent flow.
We're going to use a kitchen sink faucet to demonstrate the difference between turbulent flow and laminar flow. First, laminar flow. I'll turn the faucet on, and if you notice the stream of water coming out, it's a very clear stream. In fact, if I put my finger behind the stream of water, you can clearly see the image of my finger through the water. This is laminar flow, where the water molecules are basically traveling in parallel with each other and not in a turbulent or mixing fashion. However, if I turn the water flow rate up, the flow stream becomes turbulent. You'll notice if I put my finger behind the water stream now, you see the image fluctuating. This is the turbulence of the water molecules passing by. Turning the water flow up even more, you see the stream begins to blur the image of my finger. I'll have to turn it down here so I don't overfill the picture. Now we're back to laminar flow. Laminar flow, once again, you see my image of the finger clearly through the water stream. The water molecules are moving parallel to each other, and they're not obscuring the vision whatsoever. There's another indication of turbulence in a water flow stream, though this is more indicative of what's happening in the valve of the faucet than the stream itself, and that is the sound it produces. Listen very closely, and you can hear the onset of turbulence as a hissing sound in the valve. What you hear there, that hissing sound, is the turbulence of the water making its way through the valve. If I turn the flow rate down, the hissing goes away. That's indicative of laminar flow through the valve, where once again the water molecules are moving in parallel fashion to each other. They're not moving back and forth turbulently, and therefore not producing that hissing noise. Now, turbulence begins to manifest itself inside the valve before it does in the liquid stream. Reason being is the diameter of the passageway in the valve is much smaller than the diameter of the nozzle here. The velocity is therefore higher inside the valve than it is at the nozzle, and as a consequence, we see turbulence exhibit itself in the valve before we see it in the stream. So you may have seen before in the video, where as I turn the water flow up, you begin to hear a bit of a hissing sound in the valve before you notice turbulence manifests itself visually in the stream. But that's an example of laminar and turbulent flow in the water stream coming from a kitchen sink faucet.
This diagram shows how sediments are transported within the fluid flow and how the sediments are deposited from the fluid flow. The fluid can be wind, water, and ice in reality. Here we explain this model as how sediments are transported within a river and how they are deposited from the river and becomes the sedimentary rocks we see today. On the y-axis is the axis of velocity. The velocity increases from the bottom to the top. The x-axis is the axis for grain size. From the left to right, the grain size increases from clay to silt to sand to pebble and boulders. Let's look at this diagram from the top first. In the area with the color blue, it shows the erosion of particles from the riverbed, which means that it is the velocity that the river needs to pick up sediments from the riverbed. We can see that from medium to coarse sand grain size to cobble and boulder size, the velocity required to pick up sediments is increasing, which makes sense because the bigger sediments requires larger energy to pick up, and so the river flow velocity need to be greater to pick up the large sediments from the riverbed. However, if we look at the erosion velocity from the clay-sized particles, it is also greater than that of the medium sand. This is because that the clay minerals have a sheet-like structure and they have a cohesive force to stick to each other. It is really hard for the river to scoop clay minerals, which is the mud, out of the bed. So the cohesive force makes the clay and the silt particles hard to be eroded away from the riverbed. Now let's take a look at the bottom yellow part of the diagram. From the left to right, the velocity line is gradually increasing. This means that the depositional velocity for grain size from the clay size to the boulder size is increasing. So in reality, this diagram is telling us that if a river that is flowing very fast, carrying all kinds of sediments, and start to slow down, the first sediment will be the boulders and the cobbles. As the velocity gradually decreases, we will have more sediments such as pebbles, granules, sand, and to the last, silt and clay deposited. So this diagram tells us that flowing energy is the key to the capacity of sediment that a river can carry. When flow velocity increases, sediment will be picked up from the riverbed, and as the flow velocity decreases, sediment will be deposited on the riverbed. So this diagram illustrates how sediment is going to be transported and deposited from a river. So how do sediments transport in a river? What happened to them? There are sediments just floating within water, and they do not touch the bottom of the river. There are also sediments that rolling on the river beds and keep going forward in a rolling motion. There are also sediments, most likely sand. They are hopping on the riverbed. So they transport in the river for a while and land on the riverbed and hop back to floating transportation again. A lot of times, sand transportation is a combination of rolling and hopping. So there are three types of sediments transported in rivers: the suspension load, bed load, and the dissolved load. Suspension loads are the sediments that transport in a river without touching the riverbed. Bed loads are the sediments that transport in a river with rolling and hopping motions. Dissolved load are the ions and cations dissolved within the river water. So in the picture on the upper left, it shows the bed load deposit of a fast-flowing river. In the lower right picture, it shows the bed load deposit from a slow-flowing river. The fast-flowing river has a higher energy, so that its bed load deposit is of greater grain size than that of a slow-flowing river. When the river water flows within the channel, the flow velocity of the river increases because of increase of the river flux. When the river velocity increases, the energy of the river increases, so more sediments will be picked up and carried downstream. This is what happens during the flow confined by the river channel. So when the river overflows, sediments will be deposited due to the sudden lowering of the flowing velocity. A lot of sediments will immediately deposit along banks, form the natural levees. These two pictures shows that during dry season, only a small portion of the valley is occupied by the active river channels. A lot of channels are abandoned, while during floods, river channels are overflowed and then the floodplain is occupied by river again. During floods, the river is not overflowed every time. Sometimes one of the weak points of the natural levee fails. River water breaks the levee and across the threshold. The flow velocity decreases and the sediment deposit in a fan shape. This deposit is called a crevasse splay, which contains both sand and clay. Now let's talk about the different types of rivers. Rivers can be classified based on their channel forms. There are straight channels and sinuous channels. A river with a single sinuous channel is a meandering river. A river with multiple relatively straight channels is a braided river. A river has multiple sinuous channels is the anastomosing river, which is the transitional type of river between the meandering rivers and braided rivers. Meandering rivers usually develop at where is far from the mountains in the flat plains, where the topographic slope is very gentle. The sediment load in meandering rivers is small and the discharge of the river is relatively steady. In the following video, it shows why rivers are meandering and how the river meanders.
All it takes to turn a straight stretch of river into a bendy one is a little disturbance and a lot of time. And in nature, there's plenty of both. Say, for example, that a muskrat burrows herself a den in one bank of a stream. Her tunnels make for a cozy home, but they also weaken the bank, which eventually begins to crumble and slump into the stream. Water rushes into the newly formed hollow, sweeping away loose dirt and making the hollow even hollower, which lets the water rush a little faster and sweep away a little more dirt, and so on and so on. As more of the stream's flow is diverted into the deepening hole on one bank and away from the other side of the channel, the flow there weakens and slows. And since slow-moving water can't carry the sand-sized particles that fast-moving water can, the dirt drops to the bottom and builds up to make the water there even shallower and slower, and then keeps accumulating until it becomes new land on the inside bank. Meanwhile, the fast-moving water near the outside bank sweeps out of the curve with enough momentum to carry it across the channel and slam it into the other side, where it starts to carve another curve, and then another, and then another, and then another. The wider the stream, the longer it takes the slingshotting current to reach the other side, and the greater the downstream distance to the next curve. In fact, measurements of meandering streams all over the world reveal a strikingly regular pattern. The length of one S-shaped meander tends to be about 6 times the width of the channel. So little tiny meandering streams tend to look just like miniature versions of their bigger relatives. As long as nothing gets in the way of a river's meandering, its curves will continue to grow curvier and curvier until they loop around and bumble into themselves. When that happens, the river's channel follows the straighter path downhill, leaving behind a crescent-shaped remnant called an oxbow lake.
In this picture, it shows a meandering river. As the meandering river meanders, the bending of the river becomes bigger and bigger. The river channel deposit is accumulating at the inside of the curvature of the river channel. Braided rivers are characterized by multiple relatively straight channels. It usually developed at places with a high topographic slope and high discharge. The sediment load of a braided river is also high, so the riverbanks is not stable. So the riverbanks are not stable. The river switches channels very frequently. There are a lot of abandoned channels during the dry season, and during the flood season, the channel will be occupied again. The rivers are originated from the mountains. In the mountains, the river developed as braided river and carries a large amount of sediments. When the river comes to the plains, it becomes a meandering river, and the sediment load is relatively small. Where did the sediments go? Small part of the sediments are deposited in the braided river channels. The large amount of sediments are dumped at the mouth of the valley at the foot of the mountains. The deposit forms a fan-shaped deposit, which is called alluvial fan. The deposition of alluvial fan happens really fast, so a lot of sediment was just off the mountain. The grain size is large and poorly sorted. We can see a grain size change from the mouth of the valley to the distal part of the alluvial fan. The grain size is decreasing as the transportation energy decreases from the mouth of the valley to further away from the mountain. Similar process can happen when a river enters a lake or ocean. When river enters a large body of standing water, its flowing energy decreases suddenly, and the sediments start to deposit at the mouth of the river. When the river enters a lake, the sediments simply deposit in a fan shape, and the grain size decreases from the mouth of the river to the edge of the fan. When the river enters the ocean, the story becomes more complicated because the ocean has strong waves and tidal forces that can redistribute the sediments. So the coastal delta morphology presents more diversity. This figure shows the pole delta. You can see that part of the delta deposit merges to the subaerial area, and a part of the deposit is submerged into the ocean. The finer sediments are deposited as the sediments plume underwater. From the satellite image, you can see that the deposit under the water is drifted following the longshore current. So the coastal delta deposit is modified by wave and current actions. This picture shows the Ganges River delta. The delta deposit is modified by tidal currents. All the wiggle channels developed on top of a delta are tidal channels that funnel seawater in and out of the delta area during the high and low tide. However, river coastal delta is not the only depositional morphology at the river mouth. When the river does not carry enough of sediment to develop a delta, the ocean can invade it into the river valley and forms estuaries. The following video will explain why there are different depositional morphology of river mouth at the coastal areas, and what are the conditions to develop a delta.
The world is divided into two kinds of people, those with innie belly buttons and those with outies. Rivers also have innies and outies, not belly buttons but mouths. Where rivers flow into the sea, the land either pokes out or bends inward. But rivers don't have umbilical cords, so why do they have innies and outies? Well, coasts are the front lines between two opposing forces, land and water. In order for the ocean to invade the land, sea level either has to come up or the land has to sink down or be eroded away. And in order for the land to advance into the ocean, sea level either has to drop or the land has to build or be lifted up. Obviously, if sea level drops and then rises back again, there's no net gain on either side, but things get more complicated when a river joins the battle. For example, during the last ice age, sea levels fell by over 120 meters, and rivers cut deeper and deeper valleys to reach the falling seas. Then, about 18,000 years ago, warming temperatures began to melt the ice, and the now rising seas flooded river valleys around the world, creating giant estuaries and giving us the innie-riddled coastlines we have today. But when the steady landward march of the seas finally began to slow about 7,000 years ago, the coastlines around the mouths of some rivers began to gain back some ground. The key factor was was the sediments that rivers drop as their currents slow at the entrance to the sea. Where the sediment supply was big enough and the ocean was calm enough, the dropped dirt piled up, eventually forming new land that both lengthened the river and divided it in two. Dirt would continue to drop out and build up at the mouths of both channels, splitting the river again and again and again, creating a new lobe of land advancing slowly into the sea. Thus, the world's great outie river mouths, the fertile deltas like the Nile and the Yangtze that have helped foster human civilization since its birth, all came into being at just about the same time. The same can't be said for all of the world's outie belly buttons. What can be said, though, is that innies and outies, for both rivers and people, are a small record of how we came to be.
Okay, that's all about stream transportations from mountains to coast. See you next time.